Сегодня у нас на семинаре выступает профессор Мартин Oberlack из технического университета в Дармштадте с докладом, который здесь написан. Я думаю, что английский перевода не требуется, большинство по крайней мере, мысли поймут и студентов тоже.
Ну, русский вот и требует перевода.
Может быть. Пожалуйста.
Thank you very much.
Okay.
Oh, yeah, now I go over there. Okay, yeah, thank you very much. Very happy to be here again, so to say. So this time I will talk to you a little bit about new statistical symmetries identified to compute higher order multi-point statistic for turbulent shear flows. There's quite some group of collaborators. I've been working on these ideas of symmetry groups in turbulence since the mid of the 90s, and they all contributed in one or the other way. He just finished his thesis, 360 pages, full of formulas of symmetries in turbulence. These three guys essentially did some very large-scale numerical calculation of Navier-Stokes of turbulent flows, so we compared that to the theory. So that's for the minute, that's fine. So I have to sorry because some of the for the transparencies may be kind of boring for you, because very often I give talks. I give talks in front of a different audience, not in front of mathematicians. So I very often talk in front of physicists or engineers. So I have to introduce the basic concept of symmetries without any infinitesimal transformation or anything of that sort. So excuse me if that is too boring for you. I will make it quick. Then we will just review what we know from Euler and Navier-Stokes, and then we finally switch to turbulence. And presently, or for the last, say, 15 years, we have been working on the multi-point correlation. Then I will show you that this equations has some very particular symmetry which cannot be directly taken off Navier-Stokes or Euler equation. And I will show you some results from these new symmetries, and then I will give you some conclusions and we discuss some open questions. Well, that is, so to say, make it very quick. Usually the physicists like this idea of comparing the geometrical object that is symmetric to differential equation. So this is a differential equation here, and if we find a transformation here that maps a given differential equation to itself, now written in a new variable, that we call a symmetry. Later I will only talk about least symmetries. I'm not going to look at any other symmetry. Well, that is probably what most of you know. Usually I take this simple example of a heat equation and give the example of the scaling groups here. So that is scaling of space and time here. And that is an independent group here with the parameter A2, that is the scaling of the temperature. And of course, if you implement that here, this two-parameter group into the heat equation, you can cancel that. So that is a very well-known symmetry of the heat equation. The next thing I have to introduce then, of course, is what we call an invariant induced by a certain symmetry. So that is, we take this symmetry here, this two-parameter symmetry group again, and if we find a certain quantity, which here I call gamma, and delta here, and if we say takes this quantity x over square root of t, we implement this transformation here, and of course the A1 here cancels out, and of course this is an invariant under this two-parameter group here. Same thing you can do here for the temperature here. Again, define the temperature over the time to the power of something here, the ratio of A2 to over A1. You introduce the symmetry here, and you see that this is a conserved quantity. But usually I don't discuss this here, and most of the audiences I have, this of course is the infinitesimal form or the invariant surface condition in order to construct any invariant here from this type of groups. And of course below here we do have the infinitesimals. Finally, when we do have these invariants, we can usually use them to construct a reduced set of equations. So you have some kind of a reduced equation. So say if we take these two symmetries, these two invariants here, we use the gamma and the delta here as the new independent dependent variables. Of course, you rewrite this here, and if you put it in the heat equation, you get the usual reduction. That is classical result, which I suppose most of you know, but as I said before, many of the audiences I usually speak in front of do not know all the details. Finally here, symmetry breaking. Well, usually you have type of boundary conditions or other constraints that break certain symmetries. So here I simply take the example of a rod. So you have a given temperature here at this rod here, and this of course is infinitely long, so we have the T0 here at equals 0. And of course, if you now take this two-parameter group, put it into the boundary condition, of course we see that the A1 here can be still chosen arbitrarily, while the A2 has to be 0. That means that T0 here is symmetry breaking due to the boundary condition. So that is rather elementary introduction to symmetry groups. Now let's see what we do know about symmetry groups of Euler-Navier-Stokes equation. This is old stuff here. So of course we do have a translation in time. That means whether I start an experiment today or tomorrow, that is something that should be generally true for any physical law that is invariant in time. Rotation here, that means whether you do an experiment like that or you do your experiment in your lab like that, it should not matter. So essentially any physical law, whether that is classical mechanics, what I'm talking about here, or whether that is quantum mechanics or relativity, they're all independent, they're all invariant under this, essentially these two type of symmetry groups here. Well, for Euler and Navier-Stokes, we do have essentially two scaling groups. So try to remember for later, this e to the A2 is scaling of space, and of course the velocity is space over time. So you also have to scale this one here, and the pressure P here is 2A2. So that is also scaling of space, and then scaling of time. Remember here the A3 because we need that later again. Because the velocity is length over time, of course you have even minus A3 in the same here for the pressure. We have to be a little bit careful because in principle this is only true if we have zero viscosity. These two scaling groups here are essentially only true for Euler equation. You have to do some special things. But in principle, if you look at Navier-Stokes, you usually do not have this two scaling groups. You have one scaling group, which is a certain combination of this. We can discuss it later. So let's for a minute, let's assume in the limit here of infinite Reynolds number, we have two groups. Second, also only true, of course, for classical mechanics. That is what we call a generalized Galilean invariance. Let's look at a simple case here. Let's assume that the F here is simply a constant. That means this is just translation in space. So whether I do experiment here or there, that doesn't make much of a difference. If the f of t here, that of course then cancels out is also here. If we assume that the f of t is a linear function, that means you just go into a constantly moving frame, and as we know, physics or classical mechanics is independent of that. That means we have here a linear function that is a constant, and there is no pressure in here. But for incompressible flows, and that is what I'm talking about today, only essentially, this f here can be arbitrary. So that for an incompressible flow, because the density doesn't change, you can go into an accelerating or decelerating frame. Still, that is a symmetry that holds true for Euler and Navier-Stokes. But of course, if you accelerate, that means there is a pressure gradient, so to say, that balances this acceleration force. There's a few more symmetries for Euler and Navier-Stokes in reduced dimensions, so for plane flows, for axisymmetric flows. I'm not going to talk about that one here, so we skip that. So that is, so to say, the basic setting. That is classical mechanics, and the symmetries kind of tell us something very deep about classical mechanics. Now, if we want to look at turbulence, and that is, of course, what we want at some point, all these symmetries, of course, they should also be in all the statistical equations that we can write down in terms of when we look at turbulence. So if you look at the mean velocity, if you look at the Reynolds stress tensor, any quantity, and I will define that in a minute, of course should be invariant under these symmetries which were originally induced by Euler and Navier-Stokes. That is quite natural. We have to have that. Otherwise, we're no longer working in classical mechanics. We're out. So that is very important. Well, some history of symmetries in physics. Some people like that and ask me to do that. I know symmetries in mathematics are much older, but it was probably Einstein here in the 1905 paper that contemplated that symmetries in principle are the key feature of physics. Later in quantum mechanics, in the 20s and the 1920s, symmetries has been established some kind of an axiomatic basis for the physics in general, not only for quantum mechanics, but those who studied physics probably learned quite had some courses maybe on symmetries in quantum mechanics. Today, symmetries are essentially the foremost guiding principle to understand and mathematically model new physical laws. So the idea is, in statistical turbulence theory, there's two things we can naturally suggest. Well, first of all, symmetries of the fundamental equation of turbulence are to be discovered and used for its understanding. So we want to understand, do we have more symmetries in the statistical equations? And of course they are. We see it later. And if we now look at engineering turbulence models, something like the Kelvin type of models or other models, we should make sure that these symmetries are in there in these empirical models or semi-empirical models, and we should use symmetries as a guiding principle. Essentially what physicists have been doing for more than 100 years, we should try the same thing in turbulence, because there is quite of a lack of understanding. Now let me go to the notions I use in turbulence. Of course, again here, U is the velocity, P is the pressure. Now if I do look at mean quantities, so that is an average quantity in whatever sense, say if that is an ensemble average quantity or a time average quantity, I make an overbar here, do the same thing here for the pressure, and any fluctuating quantity is simply a lowercase u or lowercase p. So if you add those two here, of course, you get the original instantaneous velocity back. So that is what is used, what was originally introduced by Reynolds in 80 something. Essentially, he decomposed the instantaneous velocity into the mean and the fluctuation, of course, doing the same for the pressure, mean and fluctuation, and you can do that for any physical quantity you like. One second thing we need to look at is what we call the two-point correlation tensor. And we'll show you in a minute why this is important. So essentially what you do is you look at the velocity at given point x, and you look at maybe the same or maybe another quantity at the point x plus r. So essentially you take the measure of velocity here and you measure the velocity there, and you average this quantity. You see in a minute why this is important. Now we have to be careful. This capital H here, that is based on the instantaneous velocity, the real velocities you measure. But classically, people, engineers, physicists have done something else. They define a two-point correlation tensor based on the fluctuations. So that means they measure the velocity and take the mean velocity out. So they subtract that. Right? So they simply say, well, let me write that down here. So that is the instantaneous, that is the mean, and that is the fluctuation. You see in a minute why this distinguishing between, so to say, the fluctuation and the instantaneous is important. So the A, remember, is based on the instantaneous, so the velocity you really measure, and the fluctuations, well, you can only get if you take the mean velocity out. Well, of course, the key quantity that is needed later is what we call the Reynolds stress tensor. That is this one here. So if you usually average the Navier-Stokes equation, you get this unclosed term here. That is what we call the Reynolds stress tensor. And of course, if you have the classical definition of the two-point tensor here, when you take this one here to 0, of course, you get this one. Maybe I should write down really quick because I forgot to put that in here. So the Reynolds averaged Navier-Stokes equation usually looks like that. Minus so these terms here are the usual terms we have in Navier-Stokes equation, and this is the famous closure. That's a divergence. Yeah, that's a divergence of the Reynolds stress tensor. That is the usual closure problem of Navier-Stokes equation in case of considering it in a statistical sense. So these terms are what we have in usual Navier-Stokes, but if we do the decomposition here in the mean and the fluctuation, and you write down the equation for fluctuation, you get this unclosed term here. That is the key idea. We see that in a minute. What we can do then, of course, we can write down an equation for this one, but this is ugly, but what we usually prefer to do is, what people have been done for decades, they write down an equation for this two-point tensor. That has one key advantage. You see that in a minute. The equation for the Reynolds stress tensor has 3, depending on how you count, 4 unknowns. So you have an explosion of unknown terms. So that is, of course, the classical term. But the closure problem, if you write down a two-point version of it, so to say, if you extend the idea of fluctuation times fluctuation average at 2 points, you get an equation that has less unknowns. Then the classical, you get something we see in a minute. Well, let me first generalize this idea of this multi-point, and what you can define is something that is, the 2-point is a multi-point tensor. Now let's just look at velocity at the point x0 and so on until you have the velocity at the point xn. Now if you write down an equation for this quantity here, for this multi-point tensor, you get this type of an equation, and of course it's an infinite set of equations. So let's look at this here. So let's say the n is, oops, I didn't expect that. So we have the n equal 2 here, that is a 2-point tensor. Then we have n equals 2 here, that means we, should n equal 1 is 2 here, that means we have 3, that means we go to tensor order 3 here, that means we have to write down an equation for the 3 here, that means we have a 2 here. So that generates, because this higher order tensor also always appears in any order, so we have an infinite set of multi-point tensors. At the first place that looks rather ugly, but you can still recognize Navier-Stokes in here, right? This is the unsteady term, this is the convection term, this is pressure, that is viscosity. So this is one of the 3 possible formulations, in a sense exact formulations to describe the statistics of Navier-Stokes. And the nice thing is, it's an infinite set of linear PDEs, and the 2 other approaches I'm also mentioning here, that is the famous Hopf approach, based on the Hopf functional. We will later hear something here by Dr. Marta Waschlewczyk. And the other approach is a probability density function approach, also based on multi-point statistics, that all of them kind of have give a full description, a full picture of statistics of Navier-Stokes. The nice thing is it has a weak coupling. That means the equation which of the order n have only one order more, and that is in order to compute symmetries for this kind of a system, this is very, very nice. This one student here who just submitted his thesis, he proved that in order to compute the symmetries of this kind of an equation, you can actually go step by step through the equations. So you compute, so to say, the symmetries of the highest order, but then you have to check, well, that is all compatible to the next order. Otherwise, if you have an infinite set of equations, and you want to compute symmetries, you have a real problem. Because usually when we write down symmetries, what do we usually do? We say, well, if the x is a set of independent variables, and that usually depends on all independent, and the y, say, that is the vector of all. So that is the transformation here. So that is a vector of all independent, that is the vector of all dependent variables. Now if that is infinite dimensional, you can imagine that is a real problem to find such a symmetry. That is a real problem. So the nice thing about this formulation here is, and he proved that in his thesis, that you can still compute symmetries of this infinite system, because, well, we do it of course in infinitesimal form. The dependence here is strongly reduced. You can show that the dependencies are strongly reduced. So that only that allows us to compute symmetries.
Excuse me, so does it mean that y depends only on, for example, when we look for symmetries for nth order, then it depends only on n plus 1?
Exactly, exactly. That is the key result. Yeah, yeah. Now, remember that here, that is, so to say, the way we do it. So to say, we work on this instantaneous, but classically, if you look at the literature for two-point correlation tensor, you will find only this formulation here. There's always based on the fluctuation quantities. Now, if you do that, so if you write down the equation for the multi-point correlation tensor based on the fluctuations, it's ugly. It's a nonlinear PDE, and you have a coupling between all orders. So here you have, that is the mean velocity, here is the gradient of something, so that is a product. The same thing here. This is the Reynolds stress tensor here, in fact. That term that appears originally here in the Navier-Stokes equation, the average Navier. So it's a very ugly equation. So the point is, or the key point is, don't use this equation. This is extremely ugly. It's nonlinear, it's infinite dimensional, never use it. Unfortunately, when you look in the literature, you will find this equation instead of this one. But the nice thing is, there's of course, there is simple relations. And it's bijective. That means once you have the H, you can construct the U and the R, and vice versa. You can see it's highly nonlinear, still is do. So whatever you do this one here. The physics is the same as this one here. Of course, because people are used to that. Whenever we show results, usually, so to say, we take these quantities because the relation is unique. Now what's that question? Now let's look at the first very simple symmetry you can generate for this equation here. This equation here is linear. And every term here is just a derivative. That means you can add an arbitrary constant to all of the h's. And the same thing you can also do for the I here. You can add a constant d, and here for the h, of course, different ones to the a's. That means you have a rather simple, but this is a translation, so to say, the function space, or sometimes they call it a vertical symmetry. It's almost trivial, you can guess it in a sense, but later we will see this type of a symmetry is the key gradient in many of the scaling behavior we know in turbulence. We've known for a long time, some of them, like the log law, was first discovered in the 30s. This is an absolutely crucial symmetry. And this is not part of Euler of Navier-Stokes. It's not in there. It's a purely statistical quantity because it's a property that is only in this multi-point equation. We do see later that you find this type of symmetries in all the other statistical approaches. Hopf equation, Lantern functional, Lantern PDF equation, they're all there. Of course, once you have this formulation, you can back to this R formulation that you find usually in literature. So this is one symmetry here. The second one I would like to show you is essentially the scaling symmetry. This is an infinite set of equations, but still is linear, and for linear equations we know they have a scaling group. So what you can do is you can rescale any of these tensors here with a factor I call e to the power of as, and the same thing here for this pressure term. And that of course is just one, this is just one group, while this in principle is an infinite number of groups, because this one here is, so to say, a different constant for any tensor order. Here this is just one group for all tensors. We see later this is an important property to derive higher order correlations. Still, this is a scaling group that is not part of Euler-Navier-Stokes. Euler-Navier-Stokes, Euler has two groups, two scaling groups, nothing else. This one here has one more. Yeah, well, this is essentially, we recently found many more symmetries actually in this type of an equation. I'm not going to show you all the details, as I would run out of time. What we did is the following. We looked at canonical flows because, as you know, symmetries and the resulting invariant solutions, they're usually only valid for simple geometries. If you construct an engine, symmetries will usually not help you. But if you look at canonical behavior, canonical problems, so we look at the channel flow here, that means we have a pressure gradient driving a turbulent flow here. We have what we call a boundary layer flow, that means you have a plate here that is infinite size here. Then we look at a couple of rotation flows, that means we have a pressure driven flow here, but if you rotate it, that of course induces here a cross flow. And finally we look also recently, we did some DNS on transpirating flows. That means we have a pressure driven flow and we have porous walls, we do inflow here from below and a suction here from above. The result you will later see, what we did is for many of these flow cases, we did what I just mentioned, the phrase DNS, that stands for direct numerical simulation, and it is meant of the Navier-Stokes equation. So this type of flows, not showing any of the numerics here, that you have to do on supercomputers. You usually try to do as possible, large as possible Reynolds number. So right now we have one calculation running, that is not on here. That is what we call a quad flow, that one has a moving wall that is running on a supercomputer in Germany, and it has about 10 to the 11 degrees of freedom. So 10 to 11 grid points. And then you let that run for a couple of months on a supercomputer, and then you do the statistics. So it's more like a numerical experiment. You can do very nice statistics, and then you get mean velocities, you get correlations, and all that you can compute from these enormous data sets. I mean, there are terabytes of data sets. Because several of these things, I mean, we don't do experiments, so we use a computer, but we use these data sets to compare now the data from the Navier-Stokes simulations and the statistics with the symmetries, and the result from the symmetry is essentially the invariant solution. That is the idea. So what I'm showing you here, that is probably most of you are familiar. This is what, you know, this characteristic form here of this invariance condition. What is important here is, remember, we do have this AS here. That was one of the scaling groups that were purely statistical. And this A1 here, that was this C there. That means this is also a statistical symmetry which you have in this multi-point tensor equation. I'm not going to write down the complete result here. you have many symmetries coming in here in this correlation tensor. From, so to say, from this simple condition here, you can derive essentially a small number, essentially 5 different scaling behaviors that are already published about 12 years ago. And now we are in a position with all these new symmetries to compute even higher order moments. So what I usually to explain you what I'm doing here, this is a boundless, so this is, we look at the near wall behavior of a turbulent flow. This is, so to say, a boundary layer type of flow. And this log law, what you can see here below, that was first published by von Karman in the 30s, 33 or something like that. Essentially empirical, it's kind of a handmade equation. And what we do see here is this log law. I mean, they found it in numerous experiments very nicely. Well, there was some debates on whether the kappa is a constant or not, and maybe that might be slightly modified. The key point is it has been shown it's part of all engineering models, so to say. But what we see here is it's really a solution. It's a solution of the multi-point equation, so to say, the highest of the highest order correlation. And then what we did is we constructed, so to say, we started to construct the lower order solutions that are possible. Originally, these things were essentially coming from empirical equations and purely dimensional analysis. So the idea here is symmetry breaking. So if you say that let's look at the groups we have for the velocity, and we just concatenated here all the groups, the scaling groups. You put that in here, saying, well, in the near wall region we have something what Pruntle and von Karman, what they call the wall friction velocity. Essentially, you have a symmetry breaking due to this velocity here, which is in fact a stress. And if you use that in the invariant solution, you get this classical one. Well, there is exactly now. The key point is what we can do is we can write down also now the invariant solutions for the stresses of the higher order correlations. That is what you can see here. In fact, here now the results are no longer, they're written now in this fluctuation approach. And what you can see is here, for example, the classical log law, which is 1 over kappa, is part, of course, of this higher order solution. You can compare that to data. This is not our data. That was the data that was published some years ago. The bad news, of course, with the method so far is these turbulent scaling laws have only limited validity. I've not seen any scaling law that has a validity. So, for example, the near wall region, those who have actually looked at turbulence know, so to say, that is the log region here. And what we tried now is we computed the stresses and compared them with the data in the same region. So to say, here between maybe 30 and maybe 100 or so. So then you can compare that and you get a rather nice comparison, so to say, nice fit here to the data in both cases. We skipped that one. And that's the second case is the one here in the middle of such a quiet flow. So you have a pressure-driven flow, highly turbulent here in the middle. If you assume that the quantity that is symmetry breaking is at the first place unknown, we assume that these factors are unknown. You get at the very end a scaling behavior of this form here. This is the center line velocity. This is this u tau here. The gamma here, for some unknown reason, is very close to 2. We compared this data here. So to say, what we did is we take this law here, we do the logarithm on both sides, and then we compare that to the data. So the black line here is the data, and the dots are the data from the DNS, and the line here is from the theory, essentially this power law here. It's almost close to 2, and we compare that to the data. You get an almost perfect fit here, and essentially it's valid in the center of this channel flow. You can do the same thing now for the higher order correlations. You get sometimes very lengthy formulas. This is not too bad here. In other cases, we had 2 pages of formulas for the result. Here you can also compare that now. This is the stresses here, so that is what we call the normal stress, U11, U22, U33, and the shear stress, and you get an almost perfect fit in the center of the region. Essentially, also, this is also, so to say, here, this is double log scaling, the center part. We had it on with this and just asking the question, I mean, can we understand more about the symmetries when we just do variations of the flow? And one of the variation is simply a rotation of the flow. Something we know, which are known, say, in jet engines, or the Earth, of course, has Coriolis forces. So the Coriolis force essentially changes the behavior of the flow very much. What we do observe, cranking the engine, so to say, with all the symmetries here, we do find some kind of a linear scaling behavior, and the omega here is essentially scaling what the A, again, is approximately 2, we don't know why, that is unclear. So we took the DNS data here, that's some older data, but still fine. There is also newer data, and we do find exactly this. We do find a linear scaling behavior. So if you increase rotation rate, these curves here become more and more a straight line. So what we observe here is an almost perfect linear line in the center of this flow. So this is coming from the DNS, and the scaling behavior essentially gives us linear part. Again, of course, coming closer to the walls, there is no linear behavior. Again, the scaling behavior is limited to core region here of this particle flow. You can also look at stresses. I'm not showing the formulas here. Then we did, that is a rather recent DNS. We rotated the flow about this direction here, so we look again at the center region of the flow. The flow is interesting. You can in fact construct a laminar exact solution for Navier-Stokes for this case. And what you see both in laminar and turbulent, if you increase rotation rate, the mass flux in this direction goes down. This is omega 2 here. And you induce a cross flow, so with increasing rotation rate, you become a stronger and stronger cross flow. And then it reaches a maximum and then decreases again, but in fact much slower than this one here. So for large rotation, the cross flow is always dominant compared to the actual direction of the flow where we have the pressure gradient, which is driving the flow. This is the mean velocity, so to say the result, what we see here for the core region. This is, for example, one case, a relatively small rotation rate. This is U1. This is the cross flow U3. And if you go to relatively high numbers, this is high, you get, in fact, what I just mentioned, you get a much stronger behavior for the U3, that means the cross flow, and a much weaker behavior for the actual flow. In fact, what we see is even a reverse flow from the DNS, and the scaling behavior from the group analysis gives us essentially the same. These are incredibly complicated formulas here for the stresses here, which I'm not going to show, just an example here. One of the most recent cases we looked at was this case. So we have 2 plates, a pressure-driven flow, and then you have a blowing on this one here, so it's a porous wall, blowing through this one here, and suction from above. And in fact, that was, so to say, the first prediction which we did. So we said, doing the group analysis, we said, well, it should be some kind of a log law, but not in the near wall region, so not, so to say, this region, but we should find a log law in the core region of the flow. That is essentially what the group analysis gave us. And then we did DNS, and we found exactly this. So this is, so to say, a linear scaling. This is solid line here is the log. And if you do a semi-log plot here, you see some very nice log behavior. And we did various parameter changes here. and we find this type of a scaling behavior here in so to say, in non-dimensional form. Even the stresses we could compute now in the center regions, so to say, the normal stresses here. This is also the shear stress. Also here, formulas are rather lengthy. Don't show the formulas. That is not what I'm going to show. So that is the core of the theory. Not showing all the different symmetries, what we had to use. Our aim is to essentially, so to say, develop a type of a RANS. RANS means Reynolds average Navier-Stokes equation, so to say, to derive models for this term here, which capture all the proper symmetries of Euler-Navier-Stokes. That is quite natural, but we should be careful. We should also capture the statistical symmetries. For example, this one, what is essentially, remember, that was this capital C here for the U and also the higher order correlation. This is not Galilean variance, and in fact, it was probably maybe first observed by Craignan in '65, and he called it, I think he called it random Galilean invariance. Maybe somebody has heard of that. Interesting enough, when you look at the history, in history of turbulence models, usually were developed by engineers, you find essentially all models, in fact, have this type of property. So they intuitively, without knowing anything about symmetries, they intuitively made the correct choice for the symmetries, or at least part of it. Some of the key symmetries were properly chosen. Yeah, well, higher order symmetries and new scaling, however, well, you have to put them into the models. That is, so to say, our aim. Here is, in fact, well, maybe I skipped that here, just come to the conclusions. Well, new sets of symmetries have been derived for this multi-point equation. Very often you hear talks and people talk about symmetries. They don't talk about least symmetries usually, but they say, well, turbulence is a state where we lose symmetries, but in a statistical sense we get it back. But usually they mean something like reflection symmetries or so. But in fact, they are true in a sense, but even in a wider sense, turbulence generates, in a statistical sense, many more symmetries, far beyond what we know from Euler and Navier-Stokes. There are key ingredients for classical and new scaling laws, wall turbulence, rotating, and there is many, many more. With many of the new symmetries now, we can compute higher order moments. So not only the mean velocity, you can in principle compute higher order. It's a lot of work. Most important, scaling laws are solutions of the multi-point equation. Very often, if you look in the literature of turbulence, usually by engineers or physicists, they do some kind of curve fitting. I mean, they find nice algebraic scaling or logarithmic scaling. They say, well, this is a scaling law. The point is, they don't solve an equation. The point is, what I'm trying to make here, when we find some rigorous statistical behavior of Navier-Stokes, we should try to find solution of the multi-point equation. That is important. So we generate solutions rather than do curve fitting or guessing. Yeah, well, new symmetry should be part of turbulence models. I have one PhD student whose intention is that he's going to develop a turbulence model, engineering type of model that has the proper symmetries, that can also then be used for non-canonical flows, like an airplane or whatever you like. But there's open questions. Well, still, the equations are, I mean, the one proof helped a lot, but still, we're not sure if we have computed all statistical symmetries. Also, it's geometry dependent. A complete mystery is still how to determine the parameters, such as the kappa here in this old log line. Let me go back here. There's always coming these parameters. Where are the log? Here. Very famous. 0.4, the number they find in experiments. You find it in the DNS. we do know that, since this work, we do know that the kappa is essentially the ratio of group parameters. But what makes a flow choose this 1 over 0.4? We don't know. For some cases, we have a rough idea why the numbers come, where the numbers come from, but say for the log law, it's a complete mystery. So that is something that we would like to explore further. Yeah, well, as I said before, the scaling behavior is only valid in certain regions of the flow. And that is, of course, not satisfactory, because usually when we want to solve a boundary value problem, we want to have the solution for the full range between the two boundaries. This is, for turbulence at least, a serious problem. Very often Reynolds number dependent of these things are unknown. There's many other questions. Maybe I stop here.
Thank you. Вопрос, пожалуйста.
Can you make a recommendation for experimental investigation? What kind of multi-point relations would be interesting? What should I measure tomorrow?
Oh, you will measure it tomorrow? Oh, that's a good idea. Well, I mean, in order to keep the amount of data small, and it already helps a lot, I guess, is if one limits to the 2 point. So it means you have either this quantity or this one. But if you measure, you can both compute this one and this one, because this is, of course, it has many dimensions. You see, say for a shear flow, for turbulent shear flow, plane shear flow, here that would be x2, the distance to the wall, from the wall. But still, you have all 3r. That means you have a four-dimensional problem. And that usually is both for DNS but also for measurement a problem to keep so many data. But any 2-point tensor, even if you weren't able to do all of that, is of course of any help, definitely.
Еще, пожалуйста.
Show please picture with rotation. First.
This one?
No, next.
Oh, no, first one.
My question is, if the direction of rotation is different, for example, like this.
Over x?
Yeah.
Ну там был предыдущий рисунок.
Yeah. So very important. If for different direction of rotation, very different boundary.
You get completely different.
Yeah. So if for in plane rotation, I can understand that we can neglect boundary influence.
Aha. Yeah.
But if you rotate box, it's impossible. So I don't know how you can find symmetry of this flow. In this case, I see.
Right.
But if you
Here,
rotate,
for this one here?
but for example, no, it's in,
For this case here, so essentially you have, well, let's take the computer. So essentially you have the flow that goes in here, right?
Yes.
And then you rotate it like that. In fact, there was an experiment in the middle of the 70s. They put it on a big table that was done at Stanford.
Yeah.
And they put the channel like that. So of course it's closed here, and they have the flow here, and they rotate the whole thing. We had that's a good question. So this case is not too difficult. That was relatively easy also with the group theory to get these results. That was no problem. That one here was more complicated. You see, even the equations are more complicated, and the flow behavior is, there's a strong coupling between the two flows. That is essentially, you have a pressure gradient in this direction and you rotate like that. But we also did the DNS, and the group from Aachen, we asked them to do an experiment. They did this one here. So they have a pressure gradient and this one here.
without gravity. Gravity forces.
Well, when you close
Small-
it, gravity doesn't play a role
Yeah.
because it's incompressible.
Okay.
You can take that out. So you can show that you only have the Coriolis forces
Yeah.
that change the turbulence. This case is very difficult. We were not able to give an answer from group theory. It's a mystery. It's a very strange profile I show you. So what you get, so essentially, so you rotate like that. And now if you look at, let me see, so this is the velocity here. That's not too complicated. That looks easy. But you get a very strange cross flow. And the cross flow looks like that. Very strange. So this is U3.
Слушай, а еще и туда еще. Нет, вообще.
Something of that sort. Very strange. We were not able to do anything on. We find that in DNS, but also in the experiment. So this is consistent. But the group theory, we weren't able to reproduce that. So there's many open questions.
Пожалуйста, еще вопрос. Я чуть позже.
Yeah, it's for that infinite chain of system of equation for H indices, you said that your PhD student found that there are some limitations on the type of symmetries, but did they found the whole group?
No, probably not. It's still. Well, you probably found. Well, you have to. Well, let me start the following. You looked at this equation, and you can look at it, so to say. Well, compared to Navier-Stokes, if you compute symmetries of Navier-Stokes, well, you get what I showed essentially. If you reduce dimensions, say we look at Navier-Stokes only for a plane flow or an axisymmetric flow, you find more. So he's pretty sure he found, so to say, all symmetries for the most generic case, which would be the correspondent to Navier-Stokes 3D time dependent. But if you do reduce dimensions, then you might see many, many more symmetries. And there, as I said, we are not sure about completeness. Probably we are not complete.
Пожалуйста.
What can you say about Kolmogorov-Obukhov theory of locally equal?
Yeah, that's a good question. Yeah, always people ask that. Honestly, not too much actually. I mean, if you look at it in the light of group theory, the key quantity in the Kolmogorov theory is the dissipation rate, and you can do the analysis in the light of that, and you essentially get what Kolmogorov suggested, or Kolmogorov-Obukhov. The more interesting question is if we go to higher order structure functions, right? That is the key question. And there, right now, because we have a lot of these new symmetries, I have a little bit of hope. So, but maybe not soon, but maybe the next speaker can talk about that a little bit more. Because for that, I'm not sure if everybody is familiar with this Kolmogorov theory. The Kolmogorov theory essentially says if I have the velocity at a point x plus r minus at the point x, and I take any power n and I take the average. He says this goes like epsilon r to the power n over 3. for small scales. So if you measure, if you look at small distance for small scales, unfortunately, this only works for low powers. For higher powers, this is not true. If we do look at experiments, this doesn't work. That is the bad news. So it essentially only works for 2 and 3, if n is equal to 2 and 3. That works nice. If you go to higher powers, that doesn't work. And that is what is called this intermittency effect and so on. I personally believe, looking at a different type of approach, what we learn later, looking at the Lundgren-Novikov type of approach or the Hopf approach, I have some hope that we can at some point get an idea what determines the real exponent here, which this is essentially dimensional analysis, but the turbulent statistic apparently is very different.
Еще, пожалуйста, вопрос. Давайте поблагодарим докладчика за эту часть семинара закончим.